Hello, and welcome to York Universe, the astronomy and astrophysics radio podcast written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'll be one of your hosts this evening. I'm Julie Tomei, and I'm joined by Jeremy Webb. Hi, Jeremy.
Hi, how's it going?
Doing all right, thanks. Hope you're well as well.
Same, yep.
We are broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time or Tuesday morning at 2 a.m. Universal Coordinated Time because we're still in, wait, I think it's 1 because we haven't changed time yet. 1 a.m. Coordinated Time. Um, on YouTube at York U Observatory, and this is in concert with our online public viewing program run by the Observatory team. To navigate to the live show or find out more, check out our website at www.yorku.ca/science/observatory and follow the links to OPV for online public viewing, or you can join in the chat on YouTube. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on socials, Instagram with the handle at YorkU Observatory, and on Facebook at Allan I. Carswell OBS. All of our programs are free, but if you'd like to make a donation, please head over to our website. Once again, that's www.yorku.ca/science/observatory. We certainly won't turn you away. We'll be monitoring the chat room for questions and to post content. The weather, I think, is good for having some images from the telescope tonight. I'm sure the observatory team will let me know if I'm wrong on that front. But it seemed to be nice and clear when I was outside earlier. All right. So how have you been, Jeremy?
Oh, I've been going pretty good. The busyness of the start of the semester is calming down, and so we're kind of getting into the stream of things. We're learning one of my classes is about life beyond Earth, and so searching for life in our solar system around other exoplanets. And another one is Intro to Astrobiology, which has a lot of the same themes, both of which connected to some of the things we're going to be chatting about tonight.
Yeah. So let's jump right into it. We're going to start with this week in space and astronomy history. And go ahead, Jeremy. What's your first item for tonight?
Cool. Yeah, this was a fun one, and I think one that you pointed out, and it's extra fun because it actually happened on this day in astronomy 30 years ago. Usually these things are always like around this time in the past, but this was literally October 6th, and today is the 30th anniversary of the discovery of the first exoplanet around a sun-like star, and I'll emphasize that second part, around a sun-like star. The first exoplanet ever discovered was actually around a pulsar, which is one of these rapidly rotating neutron stars. And the reason we were able to find an exoplanet around a pulsar relatively easily is because pulsars have these really strong magnetic fields. They send out these beams of charged particles, charged particles from the poles of those magnetic fields. And so every time that beam points towards Earth, um, we can see the neutron star and the relationship between, how often this beam keeps coming back towards Earth, almost like a lighthouse, uh, constantly pointing in one direction. That is a really strong, precise relationship, and you can really predict how fast a neutron star, a rapidly rotating neutron star, is rotating, down to like, seconds or even less. However, we at one point in 1992, this one pulsar was discovered that had variations or fluctuations in how often the pulsar's pole was pointing directly at us. And so from those fluctuations, we're able to infer that there was an exoplanet there. So So that was surprisingly the first exoplanet ever discovered, around a neutron star, not a typical hydrogen burning star like our sun. So give it a few years later, and then finally an exoplanet was discovered orbiting around a sun-like star. And this was found using something called the radial velocity or Doppler method, which was essentially a way of figuring out that this star had a bit of a wobble to it. So if you think of a star all by itself out in the galaxy with nothing going around it, its only motion is going to be around the center of the galaxy on its orbit in the galaxy. But if it has something orbiting around it, like a planet, it's going to have a wobble. And the reason why is a lot easier to think about when you think of maybe two stars, like a binary star system. Think of two stars, exact same mass, and it's pretty easy to visualize them orbiting around their common center of mass. You can even make it really, really simple, and that, the two stars are the exact same mass. Their center of mass is going to be halfway between them, and they could have, some nice circular orbit around this common point. But the only difference between two stars orbiting around each other and a planet and a star is their relative masses. And so one thing we typically think of planets going around a star, but really what's happening is a planet and a star are also going around their common center of mass, just like two stars would. The only difference is because planets are so much less massive than stars, that center of mass of the combined system is actually sometimes inside the host star, very close to its center. So instead of seeing this star going around a point that's far from its center, it's actually just going around a point that's inside of it. So it gives it this little wobble look. And this radial velocity method, or the Doppler method, is really a way of measuring a star's motion towards or away from us. So if it has this wobble, we can measure this periodic change in velocity. And so since this one star, this sun-like star, had this nice little wobble, it was periodic. We know it was due to a planet going around it, and we were able to infer the presence of an exoplanet. So not only was this awesome, hey, there's other planets out there going around stars, kind of like our own. That was a big eye opener and something that says, hey, there's maybe life out there. Which was particularly surprising though about this star though, or about this planet, was that it was about the mass of Jupiter. So a big Jovian-like planet, but it's very, very close to its host star, right? It has like a 4-day orbital period or something like that. So meanwhile, our Jupiter, our Jovian planet, takes something like 12-ish years, I think, to go around the sun.
Mhm.
Um, this thing's closer to its host star than Mercury is, going around it in 4 days. So it got given this term hot Jupiter, and it really challenged our idea of solar system formation. We have this idea of how we think our solar system formed, and we think that the big Jovian planets were able to form in the outskirts of the solar system because there's a lot more ice, solid material out there to build up giant planets. So how did this massive planet form so close to its host star? So yeah, it was really surprising. Um, and various theories have come up with that since that maybe it formed on the outskirts and then has since migrated in, either due to interactions with other planets, interactions with comets or asteroids, or even leftover gas. And then what even made this more exciting is that as we kept finding more and more exoplanets, we kept finding more and more of these hot Jupiters, which kind of suggests, are these the norm? Is our solar system weird? And most places, most planetary systems have a hot Jupiter. Um, and more likely, though, what's happening is this is an effect of observational bias. So and when you think about it, it kind of makes sense. It's really easy to find a hot Jupiter. It's one of the more massive types of planets that you can get. It's close to its host star, so it really induces a pretty strong wobble on it. And they're actually quite easy to find, relatively speaking, so as far as exoplanets go. So, not only are we learning more about our own solar system by comparing it to other things, but we're also having to keep in mind that there's a bias out there when we look for exoplanets. There's going to be certain types of exoplanets that are easier to find than others, and that doesn't necessarily mean they're the most common type of planet in the galaxy.
Yeah, that was certainly interesting times. Um, I started at York in like 1998, and I remember, going to astronomy club meetings where it was like, let's talk about like, is our solar system weird or what's going on here with these hot Jupiters? And it's been interesting to watch as we've, developed different methods for finding exoplanets, just how much variety there is out there in systems around stars.
Yeah, and you can imagine, especially in those, late middle to late 90s when you're only talking about, oh, we have 10 or 20 or 30 exoplanets, and that's all you kind of have to do statistics on and to think about. But now we have thousands. I think we're well over 5,000 confirmed exoplanets now with many more candidates in the bank. So, as you said, a lot of diversity amongst planetary systems, which is cool to see.
Yeah, the Kepler mission definitely was a game changer there.
Absolutely, absolutely.
And one of my classmates was working for Professor Caldwell, doing like the preliminary work before the launch of the satellite. So it's one that I've been pretty interested in keeping tabs on over the years.
Neat. Very cool.
Yeah. All right. So we'll move on to another event that happened this day, October 6th. But this one was in 1931. And this was the birth of Riccardo Giacconi, who's an Italian American Nobel Prize winning astrophysicist. He was born in Genoa, Italy, and he got his laurea, which is the equivalent of a bachelor's degree from the University of Milan. He moved to the US in 1956 on a Fulbright Fellowship to collaborate with R.W. Thompson at Indiana University and spent the rest of his career in the United States. His interest was in X-ray astronomy, and his work was foundational to the field. Um, Space-based telescopes are needed since cosmic X-ray radiation is absorbed by Earth's atmosphere. And so Giacconi worked on instrumentation for X-ray astronomy, including rocket-borne detectors earlier on, and then moving on to projects like the Uhuru satellite, and then Einstein Observatory, which was the first fully imaging X-ray telescope put in space, and then on to projects like the Chandra X-ray Observatory. He was involved in other areas of astronomy as well. He was the first permanent director of the Space Telescope Science Institute, uh, which some of you might know as the institute that handles all the Hubble stuff. So he was director from 1981 to 1993 there, and then he went on to be the director general of the European Southern Observatory from 93 to 99, during which time he oversaw the construction of the Very Large Telescope. Then from 99 to 2004, he was the president of Associated Universities, Inc., and managing the ALMA array. Um, he was a professor of physics and astronomy at Johns Hopkins University from 1982 to 1997, and then a research professor from 98 until his death in 2018. In 2002, he shared the Nobel Prize in Physics with Masatoshi Koshiba and Raymond Davis Jr. Giacconi was awarded the prize for, quote, pioneering contributions to astrophysics, which have led to the discovery of cosmic X-ray sources, end quote, where Koshiba and Davis won for, quote, pioneering contributions to astrophysics, in particular in the detection of cosmic neutrinos, end quote. In the 2000s, he was the principal investigator for a major Chandra Deep Field South project. And he died on December 9th, 2018.
Wow, that is quite the CV. My goodness.
Right? He was director at this telescope and that telescope and oversaw these things in their beginning phases.
Yeah, I always like honestly, I feel like I could probably spend weeks deep diving onto various astronomers' Wikipedia pages because you see their name in like textbooks or pioneering papers, but very rarely do I take the time to be like, all right, like where did this person come from? What did they do? What are their positions? And then you find out, I did my postdoc at Indiana University, and I didn't realize that he had actually spent time there. And
Yeah,
yeah, on one of these Fulbright fellowships, which for anyone not aware, these are dedicated fellowships that promote international collaboration and exchange, which really contributes to the diversity of different programs and different universities. And so yeah, I had no idea you spent time there. Meanwhile, I was there for 3 or 4 years.
it's
Obviously not at the same time, but
not not at the same time. You're not
no, I wasn't there in the 50s. No, no, no.
you're not pushing 100.
No, no, no.
Um,
The 2 years away.
yeah, it's interesting because in the past with these like this week in astronomy history, I kind of shied away from like the birthday shout outs.
Mhm.
But I've been doing them more lately, and I've been coming across some interesting folks that I had either only heard of, you know, in passing or hadn't heard of at all, or knew because like their contributions were so famous, but like didn't really know much beyond like, oh yeah, they're known for the Smith equivalency or whatever.
Yeah.
I just made that one up. Um,
Yeah, no, it's really amazing because yeah, again, I think I knew him from his Nobel Prize, but not necessarily the rest of the details to go with that. So yeah, it's pretty amazing.
yeah, all right.
Um, yeah, so let's
Um,
see, something else that I guess happened not on October 6th, but this week in 1846. I think this is another one you pointed out to me. The moon Triton was discovered. So this is a moon of Neptune. It was the first moon of Neptune ever discovered. And it's a big one. It's actually the seventh largest moon in our solar system. So it's pretty massive, has a pretty strong self-gravity. It actually has a thin atmosphere, which is rare for a moon. Also being rare for a moon is that it appears to be geologically active. So how do we know that? Well, most bodies in our solar system that aren't geologically active, like our moon, like Mercury, like various dwarf planets, they're heavily cratered. Right? There's craters all over the place. And these craters are left over from a period when our solar system first formed called the heavy bombardment period, where pretty much any leftover chunk of rock or ice that wasn't used to form a planet, moon, or dwarf planet, a lot of those were pretty much slamming into anything that did form, with the exception being the ones that are still in the present day asteroid belt and Kuiper belt and the Oort cloud. And so they would have covered all the bodies in the solar system with early bodies with all these craters. But then if you were geologically active, whether you had volcanoes, tectonic plates, water, wind erosion, things like that, you'd be able to kind of smooth out and get rid of all these craters like you have on Earth and how Venus did with its volcanic activity and things like that. And so the Triton appears, despite being, a moon and seventh largest moon, sure, but much less massive than our moon and than any planets, appears to have been recently geologically active. It has a pretty smooth terrain, very few craters, which was surprising. And it was only ever been studied and visited once during the Voyager 2 in the late 80s, and that was just a flyby, right? Voyager 2 didn't orbit Triton or Neptune or anything like that. So it just happened to fly by on its mission to the outer solar system and took a few pictures. But it hasn't been studied in too much detail. So really all we know is that it has this thin atmosphere, has a relatively young surface, smooth terrain, but after that, we don't know too many details. And perhaps what makes it especially exciting is that it has something called a retrograde orbit. And so what that means in terms of our solar system, if you were kind of gonna could fly up and look down on the north pole of the sun and all the planets in our solar system, Almost everything, all the planets anyway, rotate around the sun or orbit around the sun in a counterclockwise motion. And then almost all the planets rotate, the way that the Earth rotates once every 24 hours. They also rotate in a counterclockwise direction. And the moon goes around the Earth in a counterclockwise direction, and we have this significant ordered motion, is what we say. And there are a few exceptions, and Triton is one of them. Triton is actually orbiting around Neptune in the opposite direction that Neptune rotates. So if you were looking down on the whole solar system, Triton would be going around in a clockwise direction, which would be a little surprising if you imagine Triton forming around Neptune. If there's some leftover material around Triton when Neptune formed, maybe that leftover material clumped together and formed a moon. But if that was the case, it would be orbiting around Neptune in the same direction that Neptune rotates. But Triton doesn't do that. It's going almost in the complete opposite direction. And so this suggests that it is actually gravitationally captured. All right, so it's the idea being that maybe Triton formed on its own, maybe as a dwarf planet that when flying by Neptune sometime millions of years ago, maybe billions of years ago, the gravitational interaction between Neptune and Triton resulted in Triton being captured and became part of Neptune's moon system. Again, it's only a theory. It seems to match the observations, but it suggests a unique origin to Triton compared to other moons, which likely formed while Neptune was forming. So it's a cool one. There's lots to learn about it. There's a few proposed missions to visit Triton and study it in more detail, but they haven't gone past the proposal stage. So I don't think there's any official planned mission coming anytime soon. Lots to learn there, I think.
Oh, I agree. It would be great to see missions going to Neptune, to Uranus, um, get a little bit more information about those planets.
Right?
I
Yeah.
in the past, I've considered those ones the quote unquote boring ones. But that's because we know so little about them, which actually makes them all that much more interesting. And
Right? I mean, even I remember Pluto, like, poor Pluto being downgraded to a dwarf planet. But even just before the mission that went out there, what was that?
New
Oh,
Horizons?
New Horizons, yeah. So before that, the only image of Pluto was this blurry Hubble image. Everyone just kind of thought it was this boring frozen wasteland.
Yeah.
And then we actually sent a mission out there to fly by it, and they're like, "Oh wow, it's actually shows signs of geological activity," and that was completely surprising. And maybe there's a lot more going on out there. And then we've seen these moons of Jupiter and Saturn that might even host life. So I mean, I think it's all cool, but there's more reasons to go check out these worlds than maybe we originally thought.
Oh, yeah, absolutely. The outer solar system is a lot more interesting than I used to think.
Yeah, and it's so hard to study though, too, right? Like a lot of these missions to go out to travel out there can take years.
Yeah,
You
absolutely.
can't rely on solar power kind of once you get kind of Jupiter or farther out. So it's difficult. It's hard to get out there and study things. So that's part of the reason why there haven't been that many missions.
Yes. Maybe we should get to doing these things not because they're easy, but because they're hard.
There you go. That sounds like a great quote.
I feel like I heard it somewhere before.
I think we can attribute it to you. I think
Yeah.
you're
All
the
right.
yeah.
Speaking of craters, if anyone isn't looking at our YouTube feed, it's a good time to look at it because we are looking at the moon through the 1 meter telescope, and it's very pretty.
Mm.
All right. So our last item for this week in history is October 8th, 1878, and the birth of Einar Hertzsprung. So this one I had heard of. He was a Danish chemist and astronomer. He was born in Frederiksberg, Denmark. He was the son of Severin and Henriette. He studied chemical engineering at Copenhagen Polytechnic Institute and graduated in 1898. He spent 2 years working as a chemist in St. Petersburg and then studied photochemistry at Leipzig University for a year in 1901. His interest in astronomy stemmed from his father being an amateur astronomer. And so he began making observation in Fredericksburg in 1902. And over time, noticed that stars with similar spectral type could have very different absolute magnitudes. In 1909, he began working at the Guten, Göttingen Observatory under the director Karl Schwarzschild. He is best known for developing the Hertzsprung-Russell diagram, which he did in 1911. And the reason it's Hertzsprung-Russell is because Henry Norris Russell independently developed it in 1913. Hertzsprung calculated distances to several Cepheid variable stars using parallax, and so he was able to calibrate the relationship between period and luminosity that makes these such important standard candles for calculating distances, and that was a relationship that had been discovered by Henrietta Leavitt. Though due to an error, he put stars at 10 times too close. But it's one order of magnitude. In astronomy, that's fine. I'm sure
And
they figured it out. They figured it out eventually.
yeah.
Yeah, he used the relationship to calculate the distance to the Small Magellanic Cloud, though, maybe he didn't have it quite right because of his error, but it was a method of trying to calculate that, which is cool. And he worked at the Leiden Observatory in the Netherlands from 1919 to 1946, becoming the director in 1937. While he was at Leiden, Gerard Kuiper was one of his graduate students. So, all sorts of big names in astronomy in this item. He discovered two asteroids, 1627 Ivar on the 25th of September 1929, and 1702 Kalahari on the 7th of July 1924. Among many honors and awards bestowed upon him in astronomy, asteroid 1693 Hertzsprung was named after him, as well as an impact crater on the moon. And he died on October 21st, 1967.
Wow. Yeah. Okay. So we can draw straight lines here from Hertzsprung to Schwartzberg to Leavitt to Kuiper.
Yeah,
Wow.
yeah.
That's
I was like, when I go check, looking for these items, I'm like, which one's the most interesting one for me this week? And I was like, whoa, this is a who's who of astronomy right
yeah.
here.
Yeah. This is nuts. This is nuts. And so Hertzsprung Russell diagrams, they are still used today, by many people. This
Oh
isn't
yeah.
just kind of something that moved us forward a peg. This is still an actively, this relationship between luminosity and temperature. This is still foundational to a lot of the work we do today. It's
Oh,
nuts.
absolutely. To the point where, there are some people out there who make Hertzsprung Russell diagrams with people and balloons to teach the concept to people at
Oh, that's neat. That's neat.
planetariums and stuff.
Yeah. Oh, that's very cool.
Yeah, that was fun.
And
I was a red supergiant.
that's awesome. You were a red supergiant. Well, that's one of the more exciting ones. They're so bright, fun. I also thought it was interesting that he was a chemist to start,
Right?
highlighting the interdisciplinary approach to some of these things. That's cool too.
Yeah. I mean, chemistry, as I was going through my research for the show notes this week, I just kept Googling things like, what does this mean in chemistry? What does this mean in chemistry? I was like, there's so much chemistry involved in astronomy.
Right? Yeah. I
Yeah.
mean, part of the thing, one of the most interesting things is figuring out what astronomical objects are made out of. And that's a purely astronomical approach or chemistry approach to things. It's pivotal.
Yeah. All right, everyone. You're listening to York Universe. We are broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. For chat, questions, content, head over to our website, yorku.ca/science/observatory. Um, you should swing by that website and click on the menu bar for OPV, which will lead you to our YouTube channel. Tonight, you are listening to myself, Judy Tomei, and Jeremy Webb. And we've just finished discussing our this week in history. We're going to move on to a reminder that though on Monday nights we do these tours virtually, the observatory is open on Wednesdays for observatory tours. So there is one coming up this week. We are at the time of year where these things can start a little bit earlier because the days are a little bit shorter. So it's from 7 to 9 p.m. Head over to the website yorku.ca/science/observatory/outreach for more information and to book your free tickets. All right. Any other reminders you want to throw in there?
I don't think so. I think you
Okay,
covered the main ones. Yeah, nothing on my end.
that's good. Okay, so we can then dive into the news.
The news, cool. All right, I think I'm up here. Yeah, so a lot of fun. I feel like the you kind of think of astronomy and the universe and things don't change that much, but honestly, week to week these days, it always seems like there's some new exciting paper discovery out there, uh, changing the way we look at the universe. And there's one up today or one up this week, looking at rogue planets. And one particular, I think the headline was "Rogue Planet Guzzling Matter Like a Star." Uh, so, we were talking about exoplanets earlier and all the discoveries we made in the late 90s and how we're up to like 5,000 exoplanets now. Um, And this other kind of type of planet that's been discovered too is what we call a rogue planet. So something that's like the mass of a planet, something like a Jupiter or a Saturn, but it's not going around a star. It's just kind of hanging out by itself in the galaxy. And there's kind of two different ways you can kind of think of getting a rogue planet. One is that it's a failed star, right? So you had this whole cloud of gas came together, it started to collapse, it was on its way to becoming a star, and then for whatever reason it did. Maybe there wasn't enough gas there, maybe the gas wasn't able to accrete into something massive enough and dense enough to create a star, and so you're kind of just left over with this failed star, something that maybe is the same mass as a Jupiter or a Saturn, or maybe a little bit bigger. And then so you have this failed star hanging out in the galaxy. Or another way to think of it as maybe it formed the same way a planet would. And it maybe at one point did orbit around a star, but there are ways to eject planets from a planetary system. Planet-planet interactions can do that. Flying by a nearby star going by can gravitationally strip a planet from its host star, which is something I'm working on in some of my research and with planets and planetary systems inside star clusters. Um, to the point being, you can have planet mass like things on their own in the galaxy. And what's cool about this one recently discovered or recently observed is that it seems to have a disk of gas going around it, which really points towards being maybe the failed star scenario. It collapsed like any solar system in the process of formation would, but never got dense enough or hot enough to form a star. But you still had some dense, warm central object in the center, and then maybe some leftover material going around it. Um, Now, for as long as we've been observing this rogue planet or this failed star, it's been accreting some of that gas in that disk onto its surface. But all of a sudden, this accretion rate jumped recently, considerably, and it's now like accreting matter at a rate of 6 billion tons of gas per second, which is something we really have only ever seen before in stars accreting matter. The quote from the interview with one of the lead authors was that this is the strongest accretion episode ever recorded for a planetary mass object. And the very short answer is we don't know why this is happening. Like the authors suggest, it could be related to the magnetic field of this object. But it's a new thing we've never seen a planetary mass object behaving like a star in terms of its ability to accrete matter. Now, it's never going to become a star. It's never going to gain enough matter and get massive enough to undergo nuclear fusion in its core. But the fact that it can accrete matter like a star just really makes it interesting and really is opening up more doors and more avenues to consider different types of objects in our universe, which is always fun.
Oh, that is cool. I have to admit, I kind of love it when nature starts to like break down the arbitrary boxes we try to put around it.
I know. Yeah, I totally agree. One thing I say in all my classes that, human beings, we like to make boxes and put things in boxes. We create music genres when really it's just a spectrum of different types of sounds and music. And same thing for astronomy. We try to put everything in these boxes, planet, moon, dwarf planet, but I think we're just seeing it's a spectrum. You can get a bunch of weird stuff out there, and it doesn't necessarily fit into a box, or it fits into a box one day, but the next day it doesn't. So it's cool.
Yeah, I think people get too worked up about Pluto.
Right? It's just it's a big heavy round thing going around the sun, just like a bunch of other big heavy round
Yeah,
things.
my favorite example of thing nature abhorring a box is a platypus.
Yeah. Right? Yeah, this platypus just ruins everything.
It's the best. It's my favorite.
It really is.
Um,
It really
and
is.
so I like when weird things are found in space, and it's like, but wait, what? This
Yeah,
changes everything.
this
Doesn't
changes everything.
necessarily just changes of the box.
Right? Yeah. Because I mean, ideally, if you had a time machine and a magical telescope that could see everything, the really only box you could truly make is like, everything that formed the same way could get put in one box. But then what happens to them after formation? That can be random chance, that can depend on their local environment, and then they might appear or evolve as something different. So
Yeah,
since we don't have one of these magical time machines and magical telescopes to figure out how every object formed, the boxes eventually become arbitrary as we learn more and more about the universe.
yeah. Then you have interesting historical things like population one stars versus
Yeah.
population two stars.
Yeah, or planetary nebulae, which have nothing to do with
Nothing
planets.
to do with planets, but they're very pretty.
Right? Yeah, they look very nice.
All right. So my first item of news is Pioneer data being reanalyzed. So whether or not life could exist in Venus's atmosphere, specifically in cloud layers, has been a bit of a hot topic for a while. Um, it's where very Earth-like conditions exist as far as temperature and pressure. Um, and given what we've learned about conditions in other layers of atmosphere and at the surface of our sister planet, where folks, once dreamed there was this jungle utopia, um, it's also an interesting thing to think about. Life could be there, but like way up high in the clouds. A team of researchers from Caltech, Pomona, University of Wisconsin, Arizona State, and NASA have published a paper about their reanalysis of data from the Pioneer mission, which was launched by NASA in the 1970s. And the results is that the clouds contain a great deal of water. But not water like we think about it in the context of Earth, where clouds are water vapor droplets. Rather, we're looking at hydrates, so substances that have water molecules incorporated in their chemical structure. It was previously thought that Venus's clouds were mostly sulfuric acid, and there is about 22% of that, according to this study. So let's take a step back. First, the data had to be located in the archives and digitized because it was on microfilm. Apparently, that took a good deal of patience and perseverance. And then once the data were available, then I think they're available online now. So the data were taken from two instruments, the neutral mass spectrometer and the gas chromatograph. It was discovered that as the probe descended through the thicker parts of the atmosphere, the inlets that were designed for gases to enter the probe were being clogged by aerosolized particles in the clouds. This is evidenced by temporary drops in CO2 levels as the probe descended. As the temperature increased during the descent, the aerosols burned off, resulting in spikes in CO2 readings as the gases could once again enter the probe. The researchers looked at burn off temperatures of different aerosols to determine what aerosols were clogging the inlets. They noticed spikes in water at 185 degrees Celsius and 414 degrees Celsius, which corresponds with hydrates such as hydrated ferric sulfate and hydrated magnesium sulfate. They also realized that water made up about 62% of the atmosphere by mass, but again, mostly as part of hydrates, almost exclusively as part of hydrates. Sulfuric acid was also found in releases of SO2 at around 215 degrees Celsius, where sulfuric acid decomposes. So that was expected. But it was also found to be released at 387 degrees, indicating a more thermally stable sulfate compound. The spike coincided with a spike in iron, indicating the presence of ferric sulfate, which may make up as much as 16% of the aerosols in the atmosphere. And the source of iron is thought to be cosmic dust pulled into the atmosphere and then reacting with acids in the clouds. This research also solves a mystery of a discrepancy between data probes that entered the clouds to take their measurements and those that remotely scanned the cloud layer with respect to the amount of water present, as remote scans wouldn't be able to detect water bound in hydrates. So what does this mean for the possibility of life in Venusian clouds? The main argument against the idea was the scarcity of water. As it turns out, there's much more water than we previously thought. So stay tuned. More research needed.
Yeah, wow. This is awesome that they made use of such older archive data and got something new out of it. That's really cool.
Yeah, I find it really neat. We have so many missions these days gathering almost unfathomable amounts of data, and it's cool to see that we're still, there's still work being done on the rocks that came down from the moon in the 60s and 70s. There's still science to be done with uh, the data that were taken in the 70s and probes that, compared to what we're sending now, probably look pretty primitive, but the data are still useful. So I think it's really cool.
Yeah, and you can imagine too, like when we're talking about like the 70s, like at the time, like computational analysis of data was like computer programming was known as like punch cards,
Yeah,
right? So, even just you had that data, you did the best you could with the tools available in the 70s. The tools we have now to reanalyze some of this data with different methods, different theories in mind, I think is just endless in a way. And say what you will about AI, but I think being able to have some AI to maybe go through this painstaking task of converting all this archive data to usable form would be awesome.
yeah, that's a good use of AI.
Good use of AI, right? This is, obviously someone's done a lot of hard work to do this, and this is just one case. There's so many old observational plates with observational data on them that need to be digitized. All these things that could just save a lot of time, and if you had some AI that could just run it for us.
Yeah. Just thinking too, like specific to Venus, like, how many Venera probes were there?
Oh my goodness. Yeah. I mean, they didn't all last that long, but. but yeah, there are many.
Oh, but there must be so much data that could be revisited. We could learn
Yeah,
so much.
right. We really could. And I think too, and even just moving beyond Venus, but just to archive data in general. So many observations are taken with kind of just one or two goals in mind. Whoever put the proposal together had an idea to study something. They did or they didn't. They learned something and then they moved on. And then yes, that data is out there, but it's hard to find, hard to get at, hard to analyze, especially if it's a decommissioned telescope or satellite.
Mm,
So just, having all that in a easy to access way and some guidance on how to deal with it. There's just so much data there. And as we get into this, well, we're already in it, but this realm of big data, which is kind of where we're at right now, revisiting all the stuff that's in the archive, I think could be a very powerful time well spent.
yeah, especially given how difficult it is to get time on a telescope or to get a mission, you know, past proposal and built and out there. And um,
Yeah,
it could be a way to get more people
right? Yeah,
doing good science.
exactly. Cool. Okay, so moving on to some other news. This is admittedly this is beyond my a little bit beyond my wheelhouse, but it was super interesting nonetheless. So I read a little bit into it. And so it's a cosmology news, I guess. So something we're relatively certain about is that our universe is expanding. We think we know this because in every direction we look, galaxies are moving away from us, and the really farther away galaxies are moving away from us at a faster rate. If the universe wasn't expanding, we would expect kind of a random distributions of motions, but the fact that no matter where we look, the distant things are moving away from us suggests that space itself is expanding. And whether or not that expansion rate is slowing down, approaching a constant value, or even accelerating, we haven't really been able to rule that out observationally. But most studies seem to be pointing towards the expansion rate accelerating, suggesting the universe will end in some sort of big chill where everything's very, very far apart from each other, and the universe just cools in billions and hundreds of billions of years. But and the reason this expansion is happening, we think, is because the universe is currently made up of 68% dark energy, which is just named that way, the dark, because we don't know what it is and we can't see it. It's not necessarily related to dark matter in any way. Another historically horribly named thing, maybe. But space itself has energy. There's empty space has an energy density. And this is what's commonly referred to as the cosmological constant that you see sometimes in Einstein's equations. So the fact that there's this background underlying energy density in the universe seems to be driving its expansion. So as more space is created, more dark energy is created, and that's, as I said, driving the expansion. But in this recent study, they analyzed recent data from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument that actually suggests this might not be the case, this expanding at an accelerating rate. So essentially what these instruments are doing, what these surveys are doing is trying to measure how the expansion of the universe has changed over time from birth to the universe at present day. And the authors argue that the expansion isn't just due to this dark energy, due to this cosmological constant alone, but instead due to a combination of this energy density and some lightweight particle that maybe would have contributed to the expansion of the universe at early times, but not anymore. So these authors actually suggest the expansion of the universe is going to slow down, and then it's actually going to stop, and the universe will collapse back in on itself, which is sometimes called the Big Crunch. Now, within observational uncertainty, where they're still not at a point where they can rule out either scenario, but this is the first study in a while that I've seen that kind of reopened the argument for a Big Crunch. Uh, so, obviously more data is needed. We need to get these uncertainties in the measurements down to levels that we can make stronger conclusions. But it's interesting to see the big crunch argument come back into the mainstream a bit.
Oh, that is so cool.
Yeah, yeah, it's definitely particle physics that I'm not like I said, outside of my wheelhouse. They talk about lightweight axions in the universe in the early universe, but cool nonetheless.
Yeah, this is not in my wheelhouse either. Um, but I find it fascinating. It's just another one of those like, will it, won't it? We don't know.
What's it gonna do? When we'd have to wait hundreds of billions of years to find out. So,
Well, I won't be there, but
right,
hopefully someone is.
right.
Or
And
maybe not, because it might be awful. I don't know.
yeah, who knows? You might not want to be there, but
Might not want to be
it's
there.
it's a fun example though of just how the ebbs and flows of as we get new observations, theories change and evolve, and something that maybe a lot of people had ruled out that the universe was going to collapse back in on itself is now back in the discussion again. So it's interesting the way these things work out.
Very neat. So stay tuned. More research.
Right? Yeah, yeah. More research, and those
Yeah.
surveys those are still ongoing. So there's more data coming. So we should be able to learn more as more and more people dig into that data.
Yeah. How? I'm so curious. I have to look more into these surveys.
Yeah, right.
Like, how do you spectroscope dark energy?
Right.
Like, how do you take a spectrum of energy?
Right. What are they doing? What are they doing? I think the short answer is that they're using these spectrometers to study objects that are just farther and farther away at just
Okay,
incredible distances. And then they use that to infer the expansion rate of the universe at these different times.
gotcha. So it's poorly
Is
named
yeah. It's
or
misleading.
confusingly named.
Misleading, yeah. It's we're not finding the dark energy and getting its spectrum, but we're getting the spectra of other things and inferring dark
Dark
energies.
energy. Okay, that makes sense. That makes
Yeah.
sense.
At least that's my first interpretation of things. I'm like I said, I'm not deep into the dark energy surveys.
All right, more research for us. Homework for us.
More homework for us, yeah.
All right. So I have one more news to share. And this is Cassini data being reanalyzed.
Well, more reanalysis, cool.
And there's actually two of them that I found today. So a couple of new insights into Saturn's moon Enceladus are coming from reanalyzed Cassini data. So the first one comes from a paper in Nature Astronomy from researchers at, I'm going to butcher this, Freie Universität Berlin and the University of Stuttgart. This study of the ice found organic molecules that could serve as precursors to more complex biomolecules. So Cassini performed 23 flybys of Enceladus, most at a speed of about 12 kilometers per second. However, the fastest flyby was done at 17.7 kilometers per second and captured quote unquote younger ice grain samples. So these are just more freshly ejected material that was like a few minutes old, a few minutes after ejection, as compared to material that was ejected from the moon days or decades before. The dating of the older material is a little hand wavy. Because of the way the mass spectrometer worked, the organic molecules were masked by water cluster ions during the slower flybys, but at the faster speed, that didn't happen. So though it's difficult to identify exactly which compounds were present, they were described as esters and or alkalines, as well as other ethers and ethyls, which are important to the search for life beyond Earth. They also show that the hydrothermal vents, which are the likely source of these compounds, are capable of producing more complex molecules than was originally thought. The second study was done at the University of Texas using a supercomputer to model geysers on Enceladus. The paper was published in JGR Planets and shares that there might not be as much water and ice being ejected from the moon as we previously thought. Again, the data came from Cassini flybys. And this study, the altitude from the surface was more important. So one of them was done at an altitude of 49 kilometers above the surface. Ion and neutral mass spectrometer analyzed gases as it flew through the plumes, and the ultraviolet imaging spectrograph looked at light from background stars to measure the density of the plumes. And 98 plumes were identified for further study. So the researchers were from University of Texas, Austin and the Royal Belgian Institute for Space Science, and they were trying to constrain physical features of the vents. So mass flow rate, how big the ice particles in the geysers were, and the temperature that they were released into space at. Their analysis showed that the parameter with the most impact was mass flow rate. And their findings are that the mass flow rate of the geysers varied considerably between flybys, the low end being 109 kilograms per second and the high end being 486 kilograms per second. It's a decent amount of material, but lower than was originally thought. And these findings will no doubt help in planning eventual missions to this extremely interesting moon.
Oh, we kind of came full circle here, talking about how interesting the outer solar system is at the beginning of our chat and ending
Yeah.
on new discoveries of these outer moons. That's awesome. And yeah, Enceladus being one of the leading candidates for life beyond Earth in our solar system anyway. So that's exciting.
Yeah, and I mean, there's no mission currently planned to go there, though I think there are some, proposals. But it'll be interesting to like see what the results from the Europa Clipper are and see if there's any parallels to be drawn between Enceladus and Europa.
Yeah, absolutely. And just, we had Mars there a few weeks ago. We're finding more and more evidence of organic molecules in appreciable amounts on these other worlds. All signs pointing towards, at least microscopic life, the possibility of it on some of these worlds. So that's exciting. And yeah, I totally agree. If there's any parallels between some of this Enceladus and Europa data, incoming Europa data, that'll be really fun.
Yeah, and once again, it's a reanalysis of data. I mean, much more recent than the Pioneer probe, so
Yeah.
probably a little easier to get at that data.
Yeah.
Um, but another great example of, using what we've already collected to expand our knowledge.
Yeah. All right. And like you said, there's just so much data out there. I remember when they studied they took those first images of the black holes, M87 and Sagittarius A star. Like it was faster to fly the hard drives uh, between institutes than actually transfer the data. Just because it was so much. And that was just one observation or one set of observations. I can't even imagine how many terabytes or whatever you want to say of data exists out there in the archive that just is begging for something or someone or some AI to get it all together and find new ways to study it. So that's exciting.
Yeah. Now that internet speeds are a little higher. Um, I spent a few summers working for Professor Norbert Bartel, and when a new data set meant magnetic tape into the machine and several hours for it to load up. It was like, start the procedure, go do something else, come
Yeah.
back later. You can start your
Right.
work.
You can start your work. Yeah. And even just in the however many years I've been astronomy, like 15 something, I don't know. The difference between like running a pretty simple simulation on my laptop that maybe took a few hours, so it's kind of like, go get some coffee, have lunch, come back. Now it's something that can be done in seconds or minutes. So even from the supercomputer side of things, it's just been, or just the evolution of the laptop. we can just do so much more in so much less time that where there's going to be more and more exciting discoveries like this, I think, in the years to come.
Agreed. All right, everyone. We have reached the top of the hour. You've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Jeremy Webb and myself, Judy Tome. You can always connect with us on Instagram at York U Observatory and on Facebook at Allan I Carswell Obs. Make sure to check out our website for all the fun website content, yorku.ca/science/observatory. Thanks for tuning in. Clear skies and have a great night.
Thanks, Julie. Thanks, everyone.